Great. So for our second speaker today, we're joined by Zoe, also from the Oxford SIAM chapter, talking about heterogeneity in soft matter. Does it matter?
Hi. So yes, I'm Zoe, and I'm going to be talking about heterogeneity in poroelastic media, and particularly what happens when we apply a cyclic load to them. And this is part of the work that I've been doing in my PhD with Sarah Waters and Derek Norton. Okay, so what's a poroelastic material? Basically, a poroelastic material is made up of solid and fluid, and the solid is made up of these solid grains. So this is sort of an element of your poroelastic material. You've got these solid grains which form a solid skeleton, and then you've got fluid that fills the pores, and the pore space is interconnected. So you can kind of think of a sponge, and when you put it in fluid, then it absorbs the fluid that fills the pores. And so sort of the sponge part is the solid skeleton. And there's many poroelastic materials in our world. So the basic example is soil, which is what poroelastic theory was built on by Bio in the 1940s. But also a lot of biological tissues are poroelastic. So your cartilage, ligaments, and tendons can all be modeled as poroelastic, and also the brain. And a lot of these media undergo cyclic loading. So soil can be subject to cyclic loading from passing traffic, so like cars and trains, but also from earthquakes and waves on the seabed. And then biological tissues like cartilage, ligaments, and tendons experience cyclic loading from the daily activity that we subject them to, so walking, running, writing equations. And the brain also experiences cyclic loading from pulsating loads, which is really important for clearing metabolic waste from the brain. And a lot of these materials also exhibit material heterogeneity. So for example, you can imagine that a soil might have different layers of different types of soil, so then the soil as a whole is heterogeneous. We also know that cartilage has depth-dependent material properties, or for example in tendons, when tendons get damaged, they change their composition and their structure, which changes sort of the bulk material properties at that damage point. So then you get heterogeneous material properties. And so all that is motivating our more general question of how does material heterogeneity affect the response of a poroelastic material to cyclic loading. And we're going to look at tensile loading, so pulling our poroelastic materials cyclically. And we're interested in this because of all this heterogeneity in these poroelastic media, and that's going to affect the response. And my personal motivation is I'm trying to model tendons, and so this heterogeneity is really important in the remodeling process in things like tendinopathy. But so this is sort of the theoretical framework, and the details of that are now on archive as of last week. Okay, so let's do some maths. Let's take our poroelastic material, and we're going to assume that it deforms uniaxially, so only in the z direction. And if we write down the nonlinear poroelastic equations in a Lagrangian framework, we're doing a Lagrangian framework because seen as we're introducing heterogeneity, that gives us direct access to the material points so we can track them more easily. So this is what the governing equation looks like. And so phi here is the Lagrangian porosity, which is the volume fraction of the fluid with respect to the initial configuration, so the undeformed reference configuration. And then phi naught is our initial porosity. So this part of the equation just comes from conservation of mass of the fluid in the solid phase. Then this part is assuming that the fluid follows Darcy's law. So K here is the permeability of the material, which essentially quantifies how easily the fluid flows through the solid. And then P is the fluid pressure. Formatting didn't work. And then this equation is just mechanical equilibrium, but in terms of the fluid pressure and the effective stress. And the reason we take the effective stress is because in a poroelastic material, the fluid is always exerting stress on the solid, even when the fluid is at rest. And so that stress, that pressure P, cannot contribute to the deformation. So to model the deformation, we're interested in the effective stress rather than the total stress. So for my model, I've chosen neo-Hookean elasticity for my solid skeleton. And we're assuming that the solid grains are incompressible, but the solid skeleton as a whole is compressible through pore rearrangement. So basically, when you pour on the material, you're going to get fluid that's going to come in and fill the pores. So the volume as a whole increases, but the volume of the actual solid hasn't changed. So basically, you need a compressible elastic law for the solid skeleton, but you've got incompressible solid grains. And that's been a bit of like many discussions with my supervisors over that. And then we're just choosing Kozeny-Kalman permeability for our permeability law, and basically that means our permeability increases with porosity. Okay, and then at our z=0 boundary, we're going to apply our cyclic stress or our cyclic displacement. We'll look at both with a frequency omega. And we're also assuming free flow at this boundary, so the fluid can come and go freely. And then at the z=1 boundary, we're imposing no flux and no displacement. So that's our system. We still need to introduce some heterogeneity. So if this is our stress law, which is some function of phi, for us it's neo-Hookean elasticity, but it could be anything that you want, and I'm calling M the stiffness, then I'm going to damage my stiffness by decreasing it locally like this. So I'm going to choose a location for the damage, L, and then I'm going to give it a magnitude of damage to damage it at z=L by magnitude D. And those are parameters that we can play around with. Yeah, and the stiffness is non-dimensionalized. Okay, so I'm going to show you some results now, and just a little bit of notation. I'm going to be looking at the strain response, which I'm writing as U sub Z. And in this uniaxial setting, the strain is equal to the normalized porosity, which is the porosity minus the initial porosity. So that's just because we're in a uniaxial deformation. But I'm highlighting this because sometimes I'll be talking about the strain and sometimes I'll be talking about the porosity. They're the same thing. It's just that intuitively, sometimes it's easy to make sense of it thinking about strain, and sometimes it makes more sense thinking about porosity. I'm also going to look at the relative fluid flow, basically just the flux. I've written the mathematical expression just in case you're curious. That's just the fluid and solid velocity. And then I just wanted to highlight as well, this is the governing equation where I've plugged in the mechanical equilibrium now. And this is a nonlinear advection diffusion equation for porosity or strain. And so the advection term comes in when your stiffness is non-uniform, so you get an additional term. But we're not too worried about that. What's more important here is the system is diffusive, and that's going to sort of help us understand the results. Okay, so I'm going to show you a few videos of we're applying a stress at a frequency omega = 10, so sort of a moderate frequency. And I'm going to show you some videos of the strain or the porosity, same thing here, against Z, so against the position. So starting with the homogeneous case where we've just got a homogeneous stiffness, so sort of our base case. So you're seeing the strain is increasing at Z=0 where it's being pulled, and then basically it diffuses down into the system. So on average, the strain is greater at Z=0, and then it's smaller at Z=1. But of course, that depends on the point in the cycle. So that's just on average. Now, what happens if we damage our stiffness? So introduce a decrease in the stiffness here at L = 0.25, and I've damaged it by D = 0.35, and in red is going to be the damaged curve. No. Okay, so you're seeing an increase in the strain about the damage point, which makes sense because you've decreased the stiffness locally and you're still applying the same stress, so you'd expect the material that it's weaker there, it's going to stretch more. And if we move the location of our damage, then the location of that increase in strain moves with the damage. Okay. So that's great, but what if we sort of want to characterize this in a little bit more of an efficient manner rather than having to run through a bunch of simulations? So for that, I'm going to define the cumulative strain and the cumulative flux. So by that, I'm going to take the absolute value of the strain and integrate it over all time, and same with the flux. So for an applied stress, the strain is always positive, so taking the absolute value doesn't actually change anything. But for the flux, it's important because basically, as you put on the material, you get fluid that comes in, and as you let go, fluid exits. So you're getting positive and negative flux. And once you've settled down to steady behaviour, the positive and the negative flux cancels out. So if I just integrated the flux over time, you wouldn't see any effect. And obviously, that's just not going to capture any of the effect from damage, which is why we take the absolute value. And additionally, this also means that this metric is cumulative. So the more cycles we run, the greater the cumulative strain and the flux are going to be. So the quantities are tied to the number of cycles that we choose. Okay, so this is what we get if we plot the cumulative strain and flux for the case that I was just showing you, the applied stress with omega equals 10. So in orange are the damaged ones, with the darkest one being damaged nearest to the boundary, the loaded boundary, and then lighter is further away, and then the dotted grey is just the undamaged case. And so you can see the cumulative strain is really highlighting that increase in the strain about the damage point. But then the cumulative flux really isn't particularly affected by the damage, maybe a little bit for this damage near the boundary, but overall, compared to the cumulative strain, the effect is really small. And so basically, using this metric, rather than having to look at 3 different videos and compare them to the homogeneous case, we're able to quickly conclude, okay, the strain is affected, the flux not really, and move on. And we can do the same for an applied displacement. So instead of applying a stress, we apply displacement. And it's quite different to what we saw for the stress, which you might expect. It's a different boundary condition. But basically, without going into too much detail, when you apply a displacement, you're imposing that displacement regardless of the material parameters. So it needs to achieve that anyway. So basically, the strain doesn't really change. But then when it gets to that damage point, it no longer requires as much stress to achieve that imposed displacement because it's weaker there. So you get a decrease in the stress there. And then the flux depends on the pressure gradients, which is equal to the stress gradients in our poroelastic material. So then the flux gets affected. And then because, yeah, I mean, I won't go into the detail of why it looks exactly like that, but that's basically why it changes. Yeah, so we were able to sort of quickly conclude how the response is affected by heterogeneity just by looking at these. But still, we've only looked at a specific set of parameters, and what we'd really like to do is vary loading frequency and damage magnitude and see what happens when we vary them without having to go through all the simulations individually. So we need to define a metric that captures the response sort of with one number. And the natural extension to our cumulative strain and flux is to define the net strain and flux, where we're also integrating it over space, so averaging it out. And so I'm going to show you some results for an applied displacement. And I'm also defining delta Q, which is the difference between the damaged and the undamaged net flux. So when delta Q is 0, there's no change between the damaged and undamaged case. When it's positive, then the net flux is increased when you damage the stiffness, and when it's negative, the net flux is decreased. And here's what happens when we vary our damage magnitude and our loading frequency. So first, we see that the net flux is increased, delta Q is positive. And then over here, we see that as you increase the damage magnitude, then the net flux increases, the effective damage increases, which is intuitive. You expect that as you crank up the damage, the effective damage is going to increase. So that's sort of good to confirm. But what we see here is the dependence on the location changes with D, which you might not have been able to capture by just sort of running through a bunch of simulations. So when D is less than 0.5, the net flux increases with the location. But then when it's greater than 0.5, it decreases with the location. And then over here, we're varying loading frequency. This vanishing porosity is just something that happens when you apply displacement too quickly to a poroelastic material. And as you can see, as you decrease the loading frequency, the effective damage really blows up. And that's basically because the flux linearizes in Z, and you're also getting a longer loading time because we fixed our number of cycles. But yeah, so we're able to sort of gain information about the system without having to go through all the simulations and capture the trends and the sensitivity to the parameters. But of course, behind these, there's also the underlying spatial and temporal information. And so this can be a really powerful tool if, for example, you have some data about a real physical problem and then you want to sort of infer information about it. So say, for example, you've got some data about the net flux in a tendon, and you know how it's been loaded. So you know, for example, if you applied a stress or a displacement, and you know the amplitude and the frequency, then you could first infer some information about the damage magnitude, maybe location as well, depending on if it's unique or not. And then from that, you could also infer information about the spatial and temporal features of the flux. Yeah, but of course there is, we do need to be careful when we're interpreting results from a metric because it's very tied, it's obviously completely tied to the definition of your metric. And to highlight that, I want to show you another example where now we're back to applied stress, and instead of decreasing the stiffness here, I'm decreasing the permeability. So a different material parameter, but we're decreasing it in the same way that we were with the stiffness. And this is the net flux, or the difference in the net flux against omega. First of all, it's negative, which you might expect because you decrease permeability, you decrease the ability of the fluid to sort of get through the solid, so the flux is going to decrease. And you have this non-monotonic dependence on omega, different to what we were seeing for the stiffness. And if we look at these two different points, so the point where the damage is maximum, and we look at what the simulation corresponds to for that, this is the flux. It doesn't look like it's changed that much. But then if I look at this point over here where the effective damage looks a lot smaller, and we look at simulations of that looks like it's a lot bigger than the other one. So, and that's just because of the definition of our metric. So basically we've fixed the number of cycles. So by slowing the loading frequency down, we're increasing the total loading time. And because this is a sort of a cumulative metric, then the more time you're running it over, then it just adds up more and more. So this ends up adding up a lot more than this one. And that's basically what that's capturing. But so there's sort of the metric and the simulation are giving you different pieces of information, and I guess what matters is what is relevant to the physical system that you're really looking into. So for example, in tendons, what really affects the mechanical function of your tendon? Is it that instantaneous response, or is it a net quantity? And so that's where the biology needs to come in and inform the model. But this is just sort of an example of a metric that you can define, and you can sort of build whatever metric you think is important in your physical system. So yeah, by defining metric, we can identify trends in the parameter space and compare across lots of parameters. We can look at different types of damage. So I briefly touched on permeability damage as well. Of course, I just looked at strain and flux, but you could look at anything that you like pressure, stress. You can also use results from the metrics to compare against real data and then infer information from your model. And as I said, the net strain and the net flux are useful tools, but they're not a replacement for the full sort of solution, because they're not capturing the full spatial and temporal features of the system. But it can be a useful guide to building more complex models, because it sort of gives us this intuition for how the parameters affects the response. And then the metrics could also be used as inputs in sort of a larger model. So for example, in tendons, we know that the cells respond to mechanical cues. And although they might not respond directly to net flux or net strain, because that's just a mathematical construct, you can correlate them. And so then you could use that in a larger model for tendons. Of course, this is limited because we did this in a uniaxial framework. So a natural extension is to go to 2D, 3D. But nevertheless, you can apply this to lots and lots of setups. So you can input any stress law that you want, any permeability law, as long as it doesn't break thermodynamics. You can play with lots of different types of heterogeneity, the initial porosity, the boundary conditions. And as I've said, I'm motivated by tendons. So at the moment, I'm trying to incorporate a tendon-specific stress law, which is harder to not break thermodynamics than I thought. And trying to then think about modifying the geometry as well of the system to look more like a tendon and play around with the boundary conditions. Thank you for listening.